That's supposed to equal 1. C sub 2 sine, what's 4 pi over 2? That's 2 pi. The sine of 2 pi, unfortunately, is 0. You can't make x pi over 2 anything but 0. I can't match that boundary condition. So in this case, no solution exists. Okay? See it right over there. Okay? Okay, so that, again, just the idea here is just to show you that, you know, when you get to boundary value problems, even the simplest type of equations, it's not obvious at the beginning that a solution exists, and if it is, if it's unique or not. Okay, but the rest of the course is all initial value problems. Okay. Now, you just have to be patient. What we're going to do now is we're going to be talking about this equation probably even into the next class, okay? And the reason for that is that we can say a lot about this equation, just the fact that it's linear, something about, you know, how to get the solution. But ultimately, what do we want to do? We want to get numbers and functions out of this, right? We want to take a concrete differential equation like that one, for example, and actually get the solution, okay? But in order to do that, we have to understand how the solution is constructed, okay? And what we're going to find out is that we're going to be looking at the homogeneous equation for a while, which is 0, and that's basically one of the stepping stones to getting the general solution. Okay, once you have, that's usually the harder part, actually, getting solution to the homogeneous equation. And what makes this fit all nice together is the fact that this is linear. So superposition will apply, as you'll see. Okay? Okay, so. So, okay, L on Y, okay, I'm going to keep that on the board. You know what that is? That's that left-hand side. Okay. Okay, L on Y is equal to 0 is called a homogeneous equation. Okay? So remember, on the left is all the stuff with the dependent variable. Everything involving Y and its derivatives goes on the left. And things that are just functions of x alone, the independent variable on the right. When the right-hand side is 0, it's called homogeneous. Very analogous to when you took linear algebra and you did remember ax equals b, right? When b was equal to 0, that was called the homogeneous equation. Okay? There's a lot of analogies between the linear algebra and linear differential equations. Okay. So when the right-hand side is identically 0, not 0 for a certain value of x, but it's identically to 0, maybe I should do something like this. Okay? Okay, it doesn't appear. That's called homogeneous. Okay? When you have L operating on Y equals g of x, not identically 0, that's called non-homogeneous. Somebody say inhomogeneous. I'm not sure. My English, you don't know what is proper. But I think the book says non-homogeneous. Okay. Okay, now this is not the book I'm going to do now, but it's a very useful concept. Thing called what's called a linear operator. Okay, and we didn't do this yet, did we? Linear operators? I don't think so. Okay, so what happens is that this idea that things are linear not only applies to linear algebra but also to linear differential equations and other areas of mathematics where things are called linear. And what we want to do is we kind of have a qualitative idea of what linear is. I want to make that more precise. Okay, basically differentiation is linear if what? You have basically L on Y equals g of x, and the thing on the left, the L on Y, only involves linear combinations of y and its derivative. Okay, let me write that more precisely, and it actually encompasses more than just that. We can call this called linear operator. Okay, and there's just two things that define it. Okay, so this is just a definition. Okay, an operator. And you know why it's an operator? It's that L part, right? It's almost like a black box. You have like an operator L, you bring a Y in there, and then what comes out? L operating on Y. You can almost write L by itself. It doesn't make any sense, though, without a Y in there. A n of x, nth derivative, plus a n minus 1 of x, n minus first derivative, dot, 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 right? And then it's basically L operates on Y to produce a function of x. Okay. So an operator L is linear if basically two conditions are satisfied. L operating on y1 plus y2 is L on y1 plus L on y2. Okay? And the second thing is that if you take L operating on alpha y of x, okay, where alpha is a constant, that equals alpha L operating on y of x. Alpha equals constant. Okay. What operators have that property? Matrices. If you took linear algebra, right, you have the operator now is this matrix A times vector x1 plus x2, you know, is ax1 plus ax2, and A operating on the vector alpha x is alpha A on x. Okay. Now, we could just do this by observation. I claim that that general nth order linear differential equation that I wrote, the operator L is linear by this definition. And why is that? It's simply because the derivative of the sum is the sum of the derivatives, right? And the derivative of a constant times the function is the constant times the derivative of the function. And you can see that's exactly what happens over here. You can just do it in your head almost. Suppose I replace y by y1 plus y2. I got an of x, nth derivative of y1 plus y2. That splits up into what? An, nth derivative of y1, plus a sub n, nth derivative of y2. Similarly for the other ones. And when you plug in every place you see y, you replace by y1 plus y2. At the end, you'll just have L on y1 plus L on y2. Yeah.
So integrals and derivatives.
Integrals also, yes, exactly. That's another good thing. Yeah, the integral operator is also a linear operator because the integral of the sum is the sum of the integrals. Very good observation. And the integral of a constant times a function, you pull it outside the integral. Yeah. Okay? And clearly, if I replace y of x every place on this left-hand side by a constant alpha y, the alpha just pulls out because the derivative of constant times a function is a constant derivative function. Okay. And this is a very good way of classifying an operator linearly in a more analytic way. Okay? Okay? So when you have a differential equation, you can either, you can use that certainly, and sometimes here, because it's so obvious, so long as the left-hand side is a linear combination of y and its derivatives, it's linear. The reason I want to introduce this notation is that it makes the discussion that will follow much, much easier. Okay, you don't have to keep writing down, plus dot, 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 dot. Okay, once you know it's L, it's an operator that's linear, it becomes very easy to do. Okay. Okay, superposition principle. This is going to be very important, okay? When we solve homogeneous differential equations, as you'll see, the idea will be to get as many solutions that are possible, okay? And we'll have to be more precise about that. For example, if we're solving a second-order linear homogeneous equation, we'll see that we have to get two solutions that are what's called independent of each other, and we'll define that very precisely in a minute, what I mean by independent, okay? And the idea is that superposition holds in that case, right? And basically, if you have one solution to the homogeneous equation, and someone gives you another homogeneous solution, any linear combination is also a homogeneous solution. Okay, that's called the superposition principle, and we'll put that, okay, I'll just keep that over here. And actually, this is done in engineering all the time. When you have a structure and it has very complicated loading, okay? What you do many times, you take each loading individually, okay? Analyze the deflection of that loading, and then say that the net deflection is the sum of those. That only applies, though, when the structure is linear, okay? And this makes it much more precise mathematically. Okay, this is called the superposition principle. If L operating on yi of x is equal to 0 for I equals 1 to, let's say, k, then L operating on, it's just summation of the, I'll do it in longhand, C1 y1 of x plus C2 y2 of x plus dot 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 plus, how many do I have? C sub k, yk of x is also equal to 0. Okay? What does says in words is that, suppose I have a differential equation like this, L1y equals 0, doing the homogeneous one now, right? And I have a bunch of functions, little y1, little y2, let's say, and you can demonstrate that the functions y1, y2, up to yk, it doesn't matter how many there are, all those are solutions to the homogeneous equation. What I claim is that if you take a superposition of those, take each y1 multiplied by an arbitrary constant and add them, then that net thing in parentheses is also a solution. That's superposition, right? Okay. How do you prove that? Let me show you how simple this is. L is a linear operator, right? By definition, L on the sum is just the following. Here's the proof. It's like 2 lines. Okay? Remember, L is a linear operator, and one of the properties of a linear operator is that L operating on the sum of 2 functions is L on y1 plus L on y2. I think you can see that extends if it's 3, 4 functions. It doesn't make a difference. Okay? So, L operating on that is just L operating on C1, y1, plus L operating on C2, y2. I'm leaving off the x dependence for short, okay? Plus L operating, let me just do it like this. I should do it a little more carefully. L operating on C1, y1, plus C2, y2, plus dot, 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 plus CK, yk of x. Because it's linear by definition, it's just L operating on C1, y1, plus L operating on C2, y2, plus dot, 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 plus L operating on C sub k, yk of x. That's just because it's linear. Well, what about the second condition of linearity? It says that if you have a linear operator and you apply it to a constant times a function, the constant pulls out. So the right-hand side is nothing more than C1, L on y1, plus C sub 2, L operating on y2, dot, 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 C sub k, L operating on yk. But we just said that all the functions, little y1, little y2, solve the homogeneous equation. So all of these guys are 0, 0, 0. So clearly L on y is equal to 0. L on that sum is equal to 0. Very easy to remember, okay? So you have a homogeneous differential equation, and somehow you come up with a set, 2 or more, depending upon the order, of homogeneous solutions, okay? When you add those with arbitrary constants, it's a solution. And this is exactly, as you'll see, the procedure we're going to do, okay? That when we actually get a solution to like a second order equation, we'll be looking for 2 functions, each of which is a solution. They shouldn't be multiples of each other because it's really the same thing, okay? And then we'll just do a linear combination, and I'll prove to you that's the most general solution of the equation, okay? Just kind of going ahead a little, okay? Let's give just some examples that the book gives, okay? And this also makes verification of solutions much easier. Once you understand this superposition principle, you don't have to take this hideous expression and plug into the differential equation. You can break it up into pieces and then show that each piece satisfies the homogeneous equation, and then by superposition, that's going to work. So here's an example. We're just illustrating the superposition principle. Suppose the function y1 of x is x squared, okay? And let the function y2 of x be x squared times the log of x. Obviously, x has to be positive. Okay? Claim y1 of x and y2 of x satisfy the following differential equation. X cubed, third derivative of y with respect to x, minus 2x times the first derivative of y with respect to x, plus 4y is equal to 0. Okay? Let's at least verify the first one. The other one is a little more messy, but we can do it over there. Okay? Again, at this point, I'm just pulling these out of the air. Okay? We haven't learned how to solve equations like this. Okay? We will at the end of the course. Okay? So I have this third order differential equation, x cubed y triple prime minus 2xy prime 4y equals 0. Just check that I copied it right. X cubed, yeah, okay. And I claim that y1 and y2 are solutions of that equation. You know how to do that. Just plug it in. let's at least verify that y1 solves, okay? Well, we know that y1 is equal to x squared, so therefore y1 prime is going to be 2x, right? y1 second derivative is 2, and clearly y1 third derivative is equal to 0, okay? Let's show that this L operating on y1 is equal to 0. Okay, what's L operating on y1? Okay, just plug in y1. X cubed, third derivative of y1. Well, that's going to be x cubed times 0, right? Minus 2x, okay? What's the first derivative of y1? That's going to be 2x. And then we need 4 times y1, which is 4x squared. Hopefully this will work out. Minus 4x squared plus 4x squared is equal to 0. Check. And you should do the same thing with x squared log x. Obviously the differentiation is a little more involved, right? But you should also show that x squared log x is a solution. Okay? What do we conclude from that? The function y of x, which is c1 x squared plus c sub 2 x squared log x, is also a solution. Right? And we don't have to do that again, right? Because by superposition, okay, we just showed that x squared is a solution. You'll show that x squared log x is a solution. And then we do the superposition principle. I know any arbitrary linear combination of x squared and x squared log x is a solution. Okay, and what's fortunate about this is we'll see that's the most general solution, as we'll show, probably next week. Okay? So the idea basically is that when you have actually we need one more. There's a third solution for that. I guess it's third order. So I take that back. But the important thing again is that the whole idea of solving these nth order differential equations will be come up with these n independent solutions, and then we'll see that the most general solution is just a linear combination of those. Haven't proven that yet. That's still to come. Okay? Okay. Let's talk now about linear dependence and independence. Okay? What I'm trying to do now is, when am I talking about linear dependence and independence? I want to make precise the fact that, solutions are quote-unquote the same. For example, you could be smart aleck about this and say, okay, x squared is a solution,